Okay, let's get started. Welcome to SYE Departmental Colloquium Series. And today we are very excited to invite Roy Dong from UIUC to give us a talk on closing the loop on machine learning, a perturbation analysis approach to decision-dependent distribution shift. Professor Roy Dong is an assistant professor in the Industrial and Enterprise System Engineering Department at UIUC. He received a bachelor's honors in computer engineering and a bachelor's honors in economics from Michigan State University. He received a PhD in EECS at the UC Berkeley, where he was funded in part by the NSF Graduate Research Fellowship. Prior to his current position, he was a postdoc researcher in the Berkeley Energy and Climate Institute, a visiting lecturer in the IEOR department at UC Berkeley, and a research assistant professor in the ECE department at the UIUC. His research uses tools from control theory, economics, statistics, and optimization to understand the closed-loop effects of machine learning with applications in cyber-physical systems, such as smart grid, modern transportation networks, and autonomous vehicles. Now, without further ado, let's give the stage to Professor Dong, and let's welcome the speaker once again.
Thank you very much for that introduction. Just to kind of give a quick research overview about who I am. I was chatting with Andy this morning, and I said this. I'm classically trained as a control theorist, which is usually the way I introduce myself. And I say it's analogous to a violinist saying they're classically trained in the Suzuki method, which is more or less like no matter what genre of music that violinist plays, there's still something about the way they hold a violin and use their fingers that you can kind of tell they've been trained in the Suzuki method. So that's kind of how I view myself as a control theorist. Broadly speaking, my work focuses on the interaction between cyber-physical systems, machine learning algorithms, and decision-making processes, and machine learning algorithms and decision-making autonomy and the behavior and incentives of agents. So anything that's the interaction of these three things. So for example, some of my earlier research studied incentive mechanisms in the power grid. So you have decision-making algorithms using advanced metering infrastructures, so that's the algorithm part. You have people deciding how to consume energy, that's the human agents part. And you have the physical component, and the cyber-physical component of the actual physical electric grid communicating, and the physical constraints presented by the group of different generators and such. So, something that's kind of intertwining these three, these tend to be my focus. I'm happy to study one or two or three of them, but broadly speaking, these are the areas I care about. And so I study cyber-physical systems, typically drawing tools from control theory. Machine learning algorithms draws tools from statistics and optimization. And human modeling draws tools from economics, game theory, and human studies. So that, broadly speaking, is what I'm interested in. But today I'm going to focus very particularly on one thrust of my research, which is focusing on decision-dependent distribution shifts. And to kind of set the stage, classically in most of your statistical learning classes, you will look at a data-generating process, basically like a fixed underlying distribution you get IID samples from, that generates data that's fed into your decision-making process, and you do things like empirical risk minimization, it really looks at this one direction. And so if you were wondering what I meant by closing the loop on machine learning, I really just mean this diagram. The idea that the outputs of your decision-making process loop around and affect your data-generating process. So if you wanted an example of this, this is like the example I really like to bring up. So decision-dependent distribution shifts in the wild. You can imagine first, we look at the data-generating process. We notice there's a correlation between higher step counts on wellness trackers like Fitbits and lower medical expenses. And so one natural decision, which we've seen deployed with some health insurance companies or some employers, we can incentivize higher step counts by offering health insurance discounts. So we noticed a correlation in the data-generating process. We made a decision from it, and the outcome of it is people start to do this. So they find ways to manipulate their step counts to increase it artificially to save money. This is a video where people talk about various ways to increase the step count. They hook things up to, a KitchenAid, I think a fan, a dog, and this is what I mean, where you make this decision and it affects the environment that stakeholders make decisions in, and as a result, you've changed the underlying data generating process. So the takeaway from this slide really is that data-driven decisions can change this underlying data generating process, and that's what I want to focus on here. And more broadly, there are a lot of societal impacts we can imagine. So a lot of the research in this area focuses on examples like classifiers that approve bank loans or make college admissions decisions. Or alternatively, when they're used to predict the probability that someone will commit crime again if released on bail. So these are impacts in the real world of these decisions that maybe actually have societal impact. So for example, if you are financially strained and you're denied bail, this can actually worsen your financial situation, which may influence whether or not you commit a crime again. So that's a lot of the real world motivation of this idea. So the outline of the talk is as follows. I might have to cut like a few of the parts a little bit short, but the optimistic goal is to get through all this. So first I'm going to go through a motivating toy example so you can see it at a technical level, motivating some of our research on it. Then I'm going to provide a quick introduction to performative prediction, which is the framework we analyze things in. Then I'm going to talk about our work looking at performative prediction through the lens of perturbation analysis. And this is the longest section of the talk. I'll be going through some control theoretic methods for understanding learning. After that, I'll talk about some more recent work extending this, looking at computational methods for verifying convergence in some settings and a smarter way to use samples. And then I'll try to close with some examples where we deploy this in simulation in some robotics settings to show what it can do. So let's go ahead and get started. A motivating toy example, we can imagine that we have a classifier that provides job offers to an applicant pool. And for each applicant, they maybe belong to group 1 or group -1. So there's two possible values for theta I. And then they have some intrinsic productivity, and that's just a normal 0-1 random variable. It's unobservable and it's independent of their group membership. And then what is observable is this noisy covariate of their actual productivity. So, you're hiring an employee, yi is their actual productivity, and y hat is maybe how much they produce on a given week, which will be a noisy observation of this. And in this model, participation by group theta equals 1 is dependent on the demographics of the offers given to the previous applicant pool. So you can really think of this as the building up of echo chambers. If you have a workplace whose culture basically has a lot of people in the group -1, it may disincentivize people from the group theta equals 1 from applying, even if they would be hired later down the road or independent of their productivity and such. So with this sort of model, and supposing the learner uses a linear classifier, with this model we can imagine this initialization. So the top row is theta equals 1 data points. The bottom row is theta equals -1 data points. Y hat is the observation we make, so we can observe their group membership and their observable productivity. And we start with a classifier that decides whether or not they get an offer. So here, everything to the right of the line gets an offer. Everything to the left of the line doesn't get an offer. And maybe we initialize this way and we learn, and eventually we learn this completely vertical classifier, which would be the fair one. But by the time this happens, group theta equals 1 has stopped applying to your company at all, right? Whereas in contrast for this model, if we started initializing the other way, we still learn that good classifier, but we still have a lively participation of group theta equals 1 in this. So this is kind of a toy example simulating this notion of decision-dependent distribution shift. And the real takeaway I want to say is initialization matters. In terms of the real-world story here, the workplace culture can be determined by the initialization of your hiring processes. And so for this model, we can simulate this and talk about what's the participation of group 1 after 600 iterations of an update rule. And you can see that there's some initializations where you still have one of the groups participating, whereas for a lot of others, they kind of just stop applying to your company. And part of why I bring this example up is some of our work is trying to understand the effects of initialization on what will happen. in comparison with a lot of the existing work, which maybe only focuses on one equilibrium or assumes there's only one optimizer, I really wanted to, a lot of our work right here is really focused on the idea that you could have different echo chambers that form. These sort of like stable points that depend on your initialization as to where your algorithm will wind up or where the overall system will wind up. So that's a toy example that motivates some of our analysis, looking at it through perturbation analysis. So next I'm going to do an introduction for performative prediction. And I guess I should have said this earlier. If anyone has any questions, feel free to just shout them out and interject. Happy to answer them if there's any part that doesn't make sense. So let's start out with a quick introduction to performative prediction. So the idea is if we make a decision X, the classical risk can be defined as this quantity here. You know, there's a loss function. My decision is lowercase x, and then there's some random variable z that has some distribution, and I'm just minimizing the expected loss with z across this distribution. This is your standard risk that you'd be minimizing in, you know, your first statistical learning class. And the modification for the performative risk is just this quantity here. So the only difference is I've added this dependency of the distribution on the decision itself. So PR here stands for performative risk, and the main jump is that that decision, the distribution of z, this random variable, depends on your decision. And so this problem is decision-dependent distribution shift has been studied under a wide variety of different names. It's kind of difficult to go through everything that's been done in it. So, you know, I'm kind of leaving my reference here if you wanted to see a more thorough talk, but some other keywords you might see for the same idea: strategic classification, endogenous uncertainty. There's a literature on this sort of idea. But the kind of new thing about performative prediction as a framework is rather than explicitly modeling this function, this mapping that eats in your decision and spits out the distribution z is drawn from. So for example, in strategic classification, you assume that people are optimizing their own utility functions, which are known. So they respond by doing a best response to your decision, and you know their utility. That's a case where you're explicitly modeling this function. And the kind of cool idea that I saw in the performative prediction paper from a few years ago is we don't assume we have a functional form for this at all. We just reason on properties of it. And so, for example, like just Lipschitz continuity or types of sensitivity conditions. So we don't assume anything about D, but from a control theoretic perspective, we actually just assume things about the gain that D can apply. And so I'll formalize that in a little bit. But you know, from a control theoretic perspective, we do a lot of things often where we don't model some static nonlinearities, or we don't model parts of our system too detailed, but rather we just kind of bound how much gain they can apply. And so this idea is what I noticed kind of underneath all of this, which motivated a lot of our study. And so this idea is about, you know, it's first introduced by this Perdomo, Zernick, Mendler, Dunner, and Mortz-Hart paper in 2020, where again, if you I think the key idea is that you don't explicitly model D. And then it's been analyzed by a few other kind of seminal works in the area. So this is the framework we're going to be building on. So to first analyze this performative risk, what we're going to do is we're going to write this function called the decoupled performative risk, which is basically it, instead of taking in one argument, it takes in two. And so the connection of the performative risk is we plug in the same argument 2 times. But if we decouple it, what that means is we have one argument that represents how x affects the loss itself. It affects the decision in the classifier, so x1. And then we have another argument, x2, that captures the distribution shift. So the reason why we call it the decoupled performative risk is that we're splitting out the 2 ways x influences what you experience. So, you know, if you change just x1, you're kind of fixing the distribution and thinking about how the loss changes for your decision, treating the distribution as fixed. If you only vary x2, you're kind of thinking about the distribution shift in isolation, ignoring, you know, how your model changes or how your decision-making changes. And so this is kind of going to be the bread and butter of how we analyze things, looking at things in terms of this decoupled risk. And to quickly motivate this, a lot of times when we look at decision-dependent distribution shift, we may not have a great model of what's going on. All we know is that people respond to our decisions in some way. and we may not have any idea how to do it, and the only way we can do it is to deploy X as a decision out there in the wild and see what people do. And so in practice, what people often do, like nowadays, is they pretend a decision-dependent distribution shift doesn't exist. So if you think about the health insurance example, a lot of these are deployed ignoring the fact that people are going to start spinning their Fitbits on a power drill. And so what does this mean in practice? They observe a data set of samples from, they deploy X, and they observe a data set of samples from the distribution dx. Then they try to improve their decision X, but they only consider the effect through the X1 argument. They fix the distribution, and they try to just optimize against that distribution, ignoring the distribution shift. So they're really essentially doing something like this. They take their current decision, and then they just go in a direction of improvement to reduce their risk, to reduce their expected loss, fixing the distribution. They just look at how their loss can be improved through the X1 argument. So this is also one of the motivations for why we're introducing the decoupled performative risk here, that we have this kind of repeated risk minimization that kind of shows up in practice. And so the idea is more or less people treat the distribution as fixed, they learn what to do, they take some descent directions, maybe one or maybe until convergence, and then they deploy things for a while with their new decision, and then they look, see if the distribution changed, and then they repeat. So the framework that often shows up a lot in performative prediction is analyzing things like this repeated risk minimization algorithm. You fix X, you get D of X, then you minimize against a fixed distribution, and then you repeat. So that's what we'll be talking about quite a bit. So with that, I want to introduce the key concepts in performative prediction here. So we say X is a performative risk minimizer if it minimizes the performative risk. So hopefully that's pretty straightforward. That's the idea that you consider the endogenous uncertainty, you consider the decision-dependent distribution shift, and you consider the model, and you consider all of this holistically, and you just try to make the best decision to make your realized risk as small as possible. You're accounting for the distribution shift completely. You're accounting for the effects of your decision on your model. And so this is, like I said, an optimal decision accounting for this distribution shift. And then a concept that is there's a nuanced difference is what a locally performatively stable point is. And so X is locally performatively stable if it minimizes this quantity. So if I think about the decoupled risk here, what this means is if I fix the distribution, I'm only optimizing across Y. And so what this means basically is if I deployed X in the wild, collected some data, looked at my loss and re-optimized, I decide to do X again. And so the idea is that if I were doing this repeated risk minimization or ignoring the distribution shift, this means I would stay there. So that's a performatively stable point. And so, like I said, it's a fixed point when we're doing repeated risk minimization. So these are the kind of two key concepts, performative risk minimization and performatively stable points. And so again, for emphasis, for the stable point, we're optimizing across Y in this equation. So X is fixed. We say X is stable if we plug in X for itself here, and then we optimize across Y, and then we get X again. So that distribution is fixed. It's not part of the optimization at all. And what's kind of interesting that was pointed out in the first paper is that these two things, you can construct counterexamples where these 2 points are arbitrarily different. You could get points where if you're ignoring the distribution shift, you can get these stable things, whereas if you're really considering holistically the whole thing, you'll get very different optimizers. So in general, you can construct counterexamples where these are as far apart as you want, but with some regularization, we can force them to be kind of close to each other. Okay, so again, kind of repeating these two concepts. Performative risk is that quantity. Decoupled performative risk is this. And we can define performative risk gradient descent as taking the gradient of the performative risk, which is essentially accounting for how this risk changes with respect to X1 and X2. And fixed points of this are the risk minimizers. And repeated risk gradient descent, which only considers the first argument. And fixed points of these are the performatively stable points. So those are kind of the key ideas. So that's my crash course in the field of performative prediction. The things I hope you take away from it are the idea of what it is to optimize accounting for distribution shift and what it is to repeatedly optimize ignoring distribution shift, and how these are essentially the two algorithms, like the two easiest algorithms to do each. All right. So with that crash course on performative prediction, I want to start talking about it now through the lens of perturbation analysis. So I'm going to actually do another crash course on perturbation analysis for those of you who don't have the exposure to this idea in control theory. So how does perturbation analysis work? So we start out with some nominal dynamics. X dot equals f of x. This describes how trajectories evolve according to some dynamics. And then we define a Lyapunov function. You can kind of think of it as an abstraction of energy. It eats in states, and it spits out a number, like how much energy is in the system at a point in time. And a good Lyapunov function basically has two things that happen. It's one, easy to show that v of x of t, so along trajectories of x dot equals f of x, this quantity as a function of time does something good. And the most typical example is the Lyapunov function goes to 0 as t goes to infinity. So we want to design a Lyapunov function where it's easy to show that this behavior does something good. And on the other hand, we want the fact that it does something good to be meaningful. So typically we want something like, if the Lyapunov function does something good, that means x converges to some optimal value or some x star. So that's actually like nonlinear systems in a nutshell, which is just the idea that we look at nominal dynamics in n-dimensional space, and instead we turn it into a one-dimensional, a scalar ODE, which is how this quantity evolves. And then we show that scalar ODEs are much easier to analyze. We show that quantity does something nice, and then we make a conclusion about the overall system. So intuitively, you can think of it like I have a system. It's really complicated to imagine how these like 5 swinging pendulums behave, but I can define an ODE that says how the energy of the system evolves, the scalar quantity. I can show the energy is decreasing, and then I can conclude that eventually the system will reach a low energy state. So that's the core idea here. And if we want to do, so this, sorry, is the next quantity here. So we look at the derivative along trajectories, which is basically essentially the chain rule. It takes in how v changes with respect to x, and then how x changes with respect to time. And so essentially this is this technically is a function that only eats in state to show the instantaneous change, but it's used to quantify the total derivative of vx of t with respect to time. So this derivative along trajectories, the Lie derivative object, is used to show that v of x of t goes to 0, and often the conditions look something like the Lie derivative is bounded by the distance from the optimizer and such. And so all that's kind of typical nonlinear systems, and if we were to apply it to perturbation analysis, the idea now is that instead of x dot equals f of x as our nominal dynamics, we have these perturbed dynamics instead. So you can think of g of x as some additional thing that perturbs the system. For example, you think of f of x as flying a plane in completely clear skies. G of x is the little bits of perturbation that turbulence give you. So you have these perturbed dynamics. And the idea for a lot of perturbation analysis is we use the same exact Lyapunov function. And the idea is that if we don't need to model the perturbation, if we can just kind of control how much energy it adds to the system, if we can keep the perturbation small in some sense, and the nominal dynamics were strongly stable in some sense, so you can picture the idea that like v dot is decreasing very strongly, that the small change caused by the perturbation doesn't detract from the fact that we can show like something good happens, like vx of t goes to 0. So the high level idea is this. There's a lot more complicated looking math, but I don't think there's anything beyond these concepts really underneath it. The takeaways are you have these nominal dynamics that in some way really strongly push you towards an optimizer or towards a desirable equilibrium. This Lyapunov function shows this, and it kind of shows how quickly it's dissipating energy, say. And then you have perturbations that maybe are injecting energy, but it's injecting energy at a slower rate than it's being dissipated by the Lyapunov function. And so we can say that this system will reject perturbations so long as g is sufficiently small because f is so stable. And the way we prove that is through a Lyapunov function. So that's my crash course on perturbation analysis. Hopefully, even without a background in control, this hopefully makes sense. And again, feel free to interject at any point in time if there are any questions about that. So let's apply this now in the setting here. So if we look at the gradient flow for performative risk, we can consider this. So, just for the purpose of this section, I'm going to do things in continuous time because it's a little easier for the Lyapunov function stuff. So I have x dot equals minus the gradient of the performative risk, which is just basically these two gradients put together. And so this is the gradient of a function. And this has really, really nice behavior. Basically, all isolated local minima are locally attractive. So in a neighborhood around, if for any x star that's an isolated local minima, there's some neighborhood around it where x of t will converge to it. And the proof is pretty straightforward. We just take the suboptimality of x as our Lyapunov function. So just the performative risk of x versus the optimal value. So that's going to be 0 at x star and positive for in a nearby neighborhood for non-optimal x. And we just take the total derivative with respect to time, like I mentioned before, and then it just winds up being this quantity. So what we have is that Vx of t is going to be decreasing across time so long as this gradient is non-zero. And it eventually pushes us to points where the gradient is 0, and that's what we can do. So if you're ever just looking in continuous time about the gradient flow, really easy to show convergence. And there's a lot of actually there's a lot of really interesting work analyzing these things, which is kind of showing that if we could actually implement these ODEs, optimization itself becomes relatively trivial. But some of the problems with algorithms is in the discretization. So depending on some of the condition numbers of this, a lot of the idea is more or less, if we could exactly implement this ODE, we could solve a lot of optimization problems. And the ones that we actually can't solve in practice are because the discretization of that ODE is ill-conditioned in some sense. So yeah, so that's the idea. If I think about just taking the gradient of the performative risk, it's this gradient flow. It's really nice. It converges to these optimal points where it optimizes the performative risk. But like I said, in practice, we might be ignoring the distribution shift. We might be doing a repeated risk minimization setting instead. So let's compare the two. And so we can define the repeated risk minimizing flow as this quantity here. Its rate of decrease is just the minus gradient of the decoupled risk only with respect to the first argument. So again, it's ignoring the distribution shift. And the thing to note is that this stops being a gradient flow because this function actually takes in two arguments. If you think of the second argument as kind of like a parameter, it's like you're constantly changing that parameter across time. So it stops being the gradient of the same function because you're not taking the total derivative of it with respect to x. So we actually can't leverage any of the previous proofs that were really straightforward to show that this converges at all directly. But like I've hopefully foreshadowed quite a bit, we can view this as a perturbed version of the gradient flow. So if I write this out, it's like the gradient of the performative risk plus this perturbation. And so we treat these as our nominal dynamics, and our perturbation is this quantity here, and then we have this x dot equals f of x plus g of x form again. And so when I think about, again, like perturbation analysis, you think about your planning, how a plane flies from origin to destination. So this is, a control and aerospace-like application. You think about how it flies in clear skies, and you want it to be so stable that kind of even near the trajectory, it starts to pull you onto this desired path. And so if you go out and fly, and so this is the stock animation I had for turbulence. This is just this image spinning around a bit. But you imagine the plane faces some turbulence. You're starting on this purple line. Some turbulence bumps you to the red part. And because you have this stabilizing force, this kind of cone that's pulling you in, you start to reject it. And even though you're not exactly following your original trajectory, you keep getting pulled to it. Because the idea is that the dynamics themselves are so stable that the perturbations don't matter. Okay. So what do we need? We basically need what do we need to apply perturbation analysis? We need the original system to be sufficiently stable in some strong sense of the word, and we need the perturbations to be small. And so if we have these conditions, that the perturbation is small enough and the original system is stable enough, then we can use the same Lyapunov function for the performative risk minimizing gradient flow that could have been used for the repeated risk minimizing flow. And so I take the same Lyapunov function, and if I differentiate along trajectories of the repeated risk minimizing flow, I get this quantity here. So for the nominal dynamics, the total derivative of this, so again, think of this as this eats in time, spits out the state, and then the v function eats in the state and spits out the energy of the system, say. And then we look at the total rate of change of energy in the system with respect to time. There's this quantity, which is what we had in the nominal case, plus this additional term here. And what we basically need to do is we need to make sure that this quantity is small. And so the first one is we can just add a condition that says, is this quantity always negative? And so if we had this satisfied, then trajectories of repeated risk minimization will converge to minimizers of the performative risk. And so we call this the performative alignment condition. The idea is more or less, it's really straightforward. So there's that additional term, and if this condition is satisfied, then the additional term is bounded by 0, and we can just have this original thing, which we can just use the previous claim to show that it converges. And so this is a formal condition that says the distribution shift doesn't hurt us too significantly. It says if I look at the inner product between these 2 points, I can kind of bound how badly they point in the wrong direction for me. And so the other kind of very interesting thing that I've hinted at before was that performatively stable and performative minimizers, they could be arbitrarily different. But with this one condition, we can actually show that ignoring the distribution shift, repeated risk minimization, can still converge to minimizers of the performative risk. So this is actually converging to points that minimize performative risk, even though we're doing repeated risk minimization. So put another way, even though we're ignoring the distribution shift, if there's this alignment condition, we'll still converge to performative risk minimizers, which I think is it's a type of result that no one's really done in the literature before, because it's kind of emphasized the idea that these two are pretty distinct. And so the next theorem is going to be really the true perturbation analysis result, which is if we let X star be an isolated local performative risk minimizer, then under some mild smoothness conditions, there's a neighborhood around X star in a radius r and a time t such that any repeated risk minimization flow starting in U will converge to a set of radius r around the optimizer, and that convergence happens exponentially fast, and then it stays there for all time afterward. And so perhaps, actually, I'm going to skip ahead. I probably should have done this first. This is the picture I want you to imagine. So here's X1 star. Here is a performative risk minimizer. And then this green set here is U. So if you start anywhere in this green set, what's going to happen is you're going to, so this blue circle here is the ball of radius R1 around the minimizer. And if you start in the green set, you're going to converge exponentially fast to within this ball of radius 1, and then you're going to stay in there forever. And so these are the types of results in control theory called ultimate bounds. So the idea is that so long as I start in the green set, I'm going to exponentially fast get into a neighborhood of the optimizer, and I'm going to stay there forever. And the idea is more or less these results are local, so you could have different local isolated optima, and you get convergence. You can get different sets for this. And so I'll go back to the theorem statement now. So that's what it is. There exists this neighborhood U, the green set, a radius r, which gave the blue set, a time t such that x of t goes to that ball of radius r exponentially fast, and then it stays in there for all future time. And furthermore, we have this vanishing perturbation condition that says that if near the optimum the perturbation starts shrinking, then we can actually get convergence to the optimal point itself, X star, and that convergence will happen exponentially fast. So we can get these types of results for how repeated risk minimization will converge to performatively stable points by treating it as a perturbation. So in contrast with a lot of the existing literature, it analyzes repeated risk minimization as a set of dynamics and performative risk minimization as a set of dynamics. To the best of our knowledge, there hasn't been many other works that have studied how repeated risk minimization could be viewed as a perturbed version of performative risk minimization, so that repeated risk minimization might actually get you performatively optimal points, which are the thing you care about. Minimizing this, like in practice, you really want that risk for the decision you make to be small. You don't just want it to necessarily be a fixed point of what happens when you ignore the distribution shift. And so this follows simply by viewing the performative aspects of learning as a perturbation. And so this can be used to characterize regions of attraction, which was kind of the original motivation of the toy example, which asks which initial conditions converge to which local performative risk minimizers or a neighborhood of them. So that's kind of what this picture signifies, which is the idea that if I start in the green region, I'll go to x1 star. If I start in this other green region, I'll go to x2 star. And again, going back to that motivating example, steady state, how much participation do we see by group 1 or group 2? So that's kind of the idea there. And so the things I swept under the rug is basically what assumptions do we need? What are the smoothness conditions? And so when can we control the gain applied by these perturbations? Well, the idea more or less is that this Lyapunov function should have a steep rate of decrease across trajectories, which I've said a few times, right? The perturbations can't affect the stability. Typical conditions look like quadratic upper and lower bounds for the Lyapunov function and linear upper and lower bounds for the derivative of the Lyapunov function. The way I think about this is it's kind of similar to equivalence of norms, the first condition, which basically says that if you show that x minus x star goes to 0, you can say vx goes to 0. And if you say vx goes to 0, then you can say x minus x star goes to 0. Because it's basically sandwiched by things up to a scaling, and it really lets you kind of interchange convergence of one with the other in the proofs. And so conditions for these, this is the sufficient curvature conditions you typically see in control theory, and these can follow from relatively typical assumptions on the loss and distribution shift. So what we do is basically, if we want to look at the performative risk at x versus the performative risk at the optimal point, we just kind of add and subtract a term here. So this is PRX, this is PRX star, and then I just add and subtract this term here, and we just control how these two terms behave. So again, just as a reminder, the first argument is how it enters the loss function, and the second argument is how it enters for the distribution shift. And so I'll just quickly go over how we control each of these. So for the first one, it's the idea that I'm fixing x1. I'm fixing the parameters of my model or my classifier, and all I'm doing is changing the underlying distribution from d of x to d of x star. And to control that quantity, we just need that the way L takes in the random variable is bounded. So supposing that this is L1 Lipschitz, that means that as the randomness in Z moves around, we have a bound on how much gain can be applied. And then we also have a bound on the Wasserstein 1 distance between these two distributions. So this is a property of the mapping D that says if I go from x to x star, the change, how far I move in Wasserstein distance, is bounded by L2 times the norm of x minus x star squared. And again, from a control theoretic perspective, all this is this notion of gains, which is the idea that if, the Wasserstein 1 distance is really nice because when you do Kantorovich-Rubinstein duality, if I feed in any L Lipschitz function f, think of that as kind of like the input, and then I kind of move from x to x star, how much gain is applied to that difference is bounded by the Wasserstein 1 distance. So as I shift from distribution d of x to dx star, the most I can amplify the Lipschitz constant is basically by the L1 Wasserstein distance. So that's the intuition behind this special case of the Kantorovich-Rubinstein duality, which is essentially if you, and this is like a trick I've found to be very useful in proving things, which is more or less that if I want to talk about how much the expectation of two functions varies as I change the distribution, the Wasserstein 1 distance is the way to do it. And so that's that quantity there. And so putting all of that together, the absolute value of this difference is going to be bounded by L1 times L2, this quantity there. It's just cascading these two inequalities, noting that I'm plugging in an L1 Lipschitz function, and the Wasserstein distance is bounded by this quantity. Pretty straightforward plugging it in, and at a high level, it's really this control theoretic mindset of I'm putting something through a bunch of operators, and I check the gain that each one applies to it. So that's how I get, that's how I bound the first term. The second term, is now I fix the underlying distribution, and I look at how the expected value of my loss changes as I change the model parameters from x to x star. I'm not changing the distribution at all, so it's kind of nice that I can kind of do something point-wise for every z, and everything works out. So supposing that it's strongly convex in x and smooth, big takeaway is basically I have quadratic upper and lower bounds for every value of z, and so I have the quadratic upper and lower bounds in expectation. Since x star is optimal, one of the gradients disappears, so I get quadratic upper and lower bounds for the second term. And so these are putting all that together, these are the three assumptions I just listed, and then I can get these quadratic upper and lower bounds that I needed to show the sufficient curvature needed. So again, these are pretty similar to the assumptions you need in the literature, and they're really just about making sure that the nominal dynamics are sufficiently well behaved. And so hopefully that gives you a strong sense of the idea of what goes underneath the proof. Similar ideas hold for bounding the norm of the gradient, but there's nothing too special about it. Again, it's just kind of looking at usually using some Wasserstein reasoning to bound what happens when you change the distribution, and then using typical like convexity or smoothness assumptions to bound what happens when we change the decision. And so from that, we get typical convergence conditions, the sufficient curvature needed. And the rest of the proof follows from typical like ultimate bounds type reasoning. So you consider the Lie derivative of the Lyapunov function along trajectories of the perturbed dynamics. When you're really far from the equilibrium, the perturbation is comparatively small, so the dynamics are dominated by the steepness of the curvature, which remember that curvature grows with the distance from x star, so it's really, really strong far from the equilibrium. And if the perturbation is small, then this is what dominates it. You get exponentially fast convergence. And then kind of close, usually what we can do is we can just take a sublevel set of the Lyapunov function and show that it's an invariant set, that if you look at the border of that level set, the vector field constantly points inward. The total derivative across time essentially points inward, or sorry, I should say the vector field points inward on the sublevel set of the Lyapunov function, so it's this invariant set. And then as a result, that means that once we're in that set, we stay there forever. We get this invariant set resulting. And actually, that last line is part of what motivated us to do this in continuous time, because invariant sets are a lot easier in continuous time because you can draw a well-defined boundary and stuff, whereas in discrete time, you can kind of hop a little bit more arbitrarily at every time step. So you put all that together, and then you get the results of this paper, which I think you have a strong sense of how to read that paper now. So we consider decision-dependent distribution shifts in the framework of performative prediction. We don't have explicit access to the distribution shift. We treat the unknown distribution shift as a perturbation or disturbance. And the classical conditions in performative prediction can be thought of as gains of the appropriate operators from control theory. And then we can translate these classical conditions from perturbation analysis into conditions on the loss and distribution map, and we can get new convergence and ultimate bounds. So the key idea is really connecting the two things there. And so we got new sufficient conditions for guaranteeing behavior from this, and in particular, conditions on which we converge to performative risk optimizers, even with repeated risk minimization. And again, I kind of hinted at this throughout. The idea is that most work typically considers a single equilibrium point, but what we're looking at is like these local regions of attraction that are quantified by these Lyapunov functions. And that might be what's worth analyzing in real-world situations where you're deploying a decision-making process and you want to know what the steady-state outcomes will be and whether or not your initialization affects that. Right. So like I said, that was the longest part of the talk, and hopefully you got the strong feeling of how I'm doing control theoretic methods to analyze learning. And I just kind of want to quickly talk about two ideas we've applied to this. So that first one is kind of like a theoretical, if a Lyapunov function exists, we can guarantee convergence. Drawing from some other tools in robust control, we can look at computational methods to find such a Lyapunov function. So what I'm going to talk about next is a computational method for verifying convergence. So the idea is we take a dissipativity approach. We can show that feasibility of a linear matrix inequality is a sufficient condition for rates of convergence. And I just kind of want to quickly do this plug that it's building on some work that came from Madison. It was Laurent Lessard was a professor here in ECE. He's at Northeastern now. And Bin Hu, whose office is a few doors down from me at Illinois, was doing his postdoc at Madison when a lot of this work came about. And the idea is more or less we're looking at systems of this form, where here we have a linear system, and the state of the linear system gets fed through a static nonlinearity delta. So static here means it has no dynamics. It's just some fixed function, which then gets fed back as the input to the state. And so to do a quick summary of classical results in dissipativity, you have linear system dynamics. Xk plus 1 equals Axk plus Buk. You have a feedback interconnection where the input is just delta applied to the state, and that's the input driving the system. And if the system dissipates energy sufficiently enough and the feedback interconnection doesn't inject too much energy, we can get convergence and convergence rates. And I just wanted to give the high level of this. So verifying this dissipativity condition that ensures convergence can be phrased as a linear matrix inequality. So if you check feasibility, you can prove dissipativity, and dissipativity implies convergence. And so the idea that came from Madison 5 to 10 years ago is that if we connect this to optimization, if we look at something like gradient descent, this actually fits really nicely into the framework where the A matrix is the identity, the B matrix is minus eta times the identity, and this feedback linearity is just the gradient of your function. And so if you just kind of plug these things in and then apply dissipativity ideas, you can phrase an LMI that says these dynamics converge at a particular rate. So that's the high level from optimization. And what we did is we extended this to performative prediction, where instead of taking the gradient, we might be taking the gradient of the performative risk in the second example, or we might do repeated risk gradient descent, which can be translated into a similar framework where the B matrix now takes in two inputs. The static nonlinearity spits out the gradient with respect to each of these arguments. So we had to extend those results to be able to take in two arguments. And, but we can apply similar ideas to show that feasibility of a linear matrix inequality implies dissipativity, which can imply a type of convergence. So that's a paper that's under second revision right now. And again, that high-level idea is, again, just treating this, the actual dynamics of the optimization, the gradients of our risk, as the static nonlinearity feeding back into a system. So the takeaway from that is instead of just saying this Lyapunov function, if we have a Lyapunov function, we have convergence. Now we say if you can solve this LMI, it gives you a Lyapunov function that can be used to verify convergence. And I have about 2 minutes left, so I'm going to try to quickly walk through this last bit. So everything thus far, we acted as though we had an oracle, which provides that distribution for a decision. So remember, this is the decoupled risk, and we take the gradient with respect to x1. We're actually exactly plugging in d of x2 here, right? We actually exactly have d of x2 when we're calculating the gradient with respect to it. And so if you think about what this means in practice, if we don't know this distribution shift, which is the whole point of this framework, we need to deploy x and make observations of the samples. And because we don't know it, we can't really simulate it. And this is kind of tricky, right? You're trying to make a bank loan decision. You pick an x, you deploy it for a month, you collect a bunch of data that gives you an estimate of d of x, and then you can update your decision accordingly. And so what we've been looking at is the idea that the deployment and getting data samples is actually much more expensive than the computation. But to kind of emphasize, most of the existing work shows convergence when you have an exact distribution oracle. When you can get d of x2 exactly at every iteration, you show convergence with that. And then you get sample complexity by basically saying, OK, well, for each iteration, how many samples do I need such that the empirical distribution is really close? And then I just kind of plug in the empirical distribution for the true distribution. At most, there's an error of epsilon with high probability, and then we get the convergence follows from the fact that if we had the exact distribution, it would follow, and if we have this many samples, we're very close to the exact distribution. And so if we think about, if we really want to be sample efficient about this, do we actually need the empirical distribution to be close? And the idea is more or less, let's stop using the empirical distribution as this plug-in estimator for the true distribution, because that wasn't really necessarily justified from a computational perspective. What we do is we use tools from distributionally robust optimization. We're just going to optimize robustly across distributions near the empirical distribution. And so I just kind of want to really quickly go through this, but what we wind up doing is we wind up minimizing this robust objective. So we just look at a ball, usually bounded Wasserstein norm around the empirical distribution we observe, and we solve this problem at each iteration instead. And we show that this actually can do things better with fewer samples. And so this is a recent NeurIPS paper that we'll be presenting in a little bit. Takeaways: each iteration is more expensive, but the hope is the idea is that in practice, collecting the data samples is what's expensive. Iterations will converge nicely. There are cases where this can be tractably calculated. We can show, some conic approximations work. And then we also get bounds on how well these limit points do compared to the optimal point. Okay, and so real quick, last thing, robotics application. Picture a robot navigating a crowd. Some of you have probably seen things like this before. It has to navigate around people accordingly, but people are wildly unpredictable. And actually, a lot of the existing work in crowd navigation treats the way people walk as exogenously given. So the idea is wherever your robot is, it doesn't influence how people walk, which can be unrealistic at times. And so skipping ahead real quick, we work on basically trying to internally model the fact that where our robot moves influences how people walk. And that's our result on the left, where we're actually accounting for the fact. So this paper is called Interaction-Aware Conformal Prediction for this setting. I've swept the conformal prediction parts under the rug real quick, but if we account for how people will respond to the robot's movements, we can get more clear paths. And so here in the middle one, this is adaptive conformal prediction, ignoring the distribution shift. These bounds wind up growing really large, and you wind up not being able to get through. And in this one, this offline setting, we are not actually able to get safety guarantees. So the idea is more or less applying this repeated risk minimization setting to crowd nav allows us to account for how a robot moving through a crowd can influence people's movements. Okay, so just a quick summary. Nowadays we have this feedback loop. What we covered was performative prediction through the lens of perturbation analysis, computational method for verifying convergence, a smarter way to use samples using distributionally robust optimization. The computational method was through dissipativity theory and linear matrix inequalities. There's applications in robotics and crowd navigation. And so real quickly, I think closing the loop on machine learning outside the scope of this talk, a lot of the directions we're looking at, when they're deployed in the real world, we need to consider data provenance, data veracity. Some work I haven't talked about here is game theoretic models of data exchange, incentives of the parties and stakeholders, the dynamic effects, which is primarily what I talked about today, and new vulnerabilities that might arise. So with that, I just have the faces of all the people that helped with this work. Thanks so much. Sorry for going a little bit over, and hopefully you enjoyed this talk. Thank you so much, everybody.
Any questions? So I have a question about the comparison. One wonderful work of using these RX1 to optimize these to show the convergence rates. So in practical scenarios, is there a reason to prefer to use these disregarding these distribution shifts compared with the optimization procedure of using PR directly?
Yeah. So there's two different sales pitches I often offer for this work. The first one is trying to analyze what happens when people pretend it doesn't exist. So like the health insurance example. People aren't thinking about step counts being influenced by power drills when offering health insurance benefits. So in some settings, people are ignoring it, and we're analyzing what happens. So that's one story to justify it. And the other is maybe in a case where you absolutely have no knowledge, maybe there's nothing better you can do. Like if you don't have the capacity and you don't have any domain knowledge to make any assumptions on what that distribution shift is, there's actually not that much in terms of algorithms. Like the performative prediction literature kind of treats this as your best bet. You kind of try to solve it, and the hope is that some of those theoretical results that show somewhat decent convergence are enough to justify it. And this is something I say a lot, which is if you have any information about the distribution shift, don't do this. Yeah. You incorporate that knowledge about the distribution shift itself. Yeah.
Yeah, wonderful. Yeah, thank you so much. Any questions?
Just a clarification, a very naive question. So in your main result, I think you provide a condition such that some good behavior happens, which you showed in a picture, yeah, that green one. Yeah, so that, yeah, you can get into a region, yeah, of radius R, and you stay there. But what's the, I mean, R could be very big, so I've not understood, yeah, I would like to understand if you, how the magnitude of R could impact the quality of this desirable behavior, or how to interpret this, yeah.
Yeah, I mean, what you said is absolutely right. If R is large, maybe this claim is weaker. Some of the details I swept under the rug were actually the expression for R, which effectively are dependent. The most impactful terms are like these three constants here, C1, C2, C3, C4. And so really I think yes, R1 bigger means weaker result, but it's really about the geometry of the problem. And so if you have like C1 and C2 are really close to each other, then that B is almost a quadratic, and then you can get more control over what that R is. So like some of these bounds are on the ratio of C2 over C1, which is very analogous to like oftentimes when we see like the smoothness parameter divided by the strong convexity parameter in optimization. Yeah, so the radius is very much so linked to the geometry of the problem. You can't do too much about that. Yeah.
Great, thanks.
Yeah. I have any more questions from the audience? Yeah, I have another question about these your approach of proof, right? So in practice, when solving this kind of problem, reparameterization trick is one way to deal with these decision dependent distributions. People just regard these dx as generated from let's say for example, normal multivariate normal random variable and transformed by a function like f. I just wonder if it's possible to apply some conditions on the function of the function of f, in replace of these, the condition on this Waterston distance between the distributions.
That's a really good question. I think if I'm understanding correctly, you're moving into the realm outside the performative prediction framework into like where you explicitly have some modeling.
Yeah.
I don't know if it's going to just, my first instinct is that's just going to reduce to kind of classical results. You can kind of eat it into the loss function, and then you just have a typical optimization problem. Where again, like here what we're doing is we're kind of looking at the uncertainty in D, we bound the gain it applies. And so what you're saying is instead of having these gain bounds, like these sector conditions, instead of having these gain bounds, we instead just replace it with some known function, which we can exactly calculate the derivative of. So my first instinct is that it would be very similar, but one of the gain terms disappears. We basically removed one block of running things through.
Yeah.
Or at least we're replacing like upper and lower bounds on the gain with like an exact gain. And I'm not sure if at that point it reduces to kind of like a classical optimization problem.
Yeah, probably, because there's a concrete function,
Yeah, and especially with like normal distributions, they're so nicely behaved.
Yeah.
Squared and second moments and stuff that it probably, there's an equivalent thing where there's no expectation and it's like still linear or something.
Yeah. Thank you.
Yeah, thank you.
Questions? Okay, let's give the speaker another round of applause. Thank you.